All right, welcome back everyone for our penultimate lesson of the semester. We're in Unit 13 now. We're going to be talking about storms and in particular looking at blizzards, tornadoes, and hurricanes as examples of some important kinds of storms. So our goals for this lesson are for you to understand how storms such as tornadoes and hurricanes form, then to be able to evaluate the consequences of these storms, and finally to identify the links between storms and climate change. So to start off our understanding of storms, we need to look at atmospheric pressure. So pressure in a general physics kind of sense is the force that's exerted by the collisions among particles. So if you've got a blob of air or of water and all the particles in it are bouncing around and they're hitting the things on either side of it or anything that's put into it, that force being exerted by those particle collisions is the pressure that that substance, that air or water or whatever is exerting. And so here we're going to be focusing on atmospheric pressure, pressure exerted by the air, and that pressure varies from place to place. And so the illustration there, I've got a little map showing air pressure across the United States and southern Canada, and it's varying, and we can measure it in units called bars. So 1 bar is approximately the average air pressure at sea level. So this is a unit that is calibrated to be useful in the context of talking about atmospheric pressure. We wouldn't really measure other things in bars. It's not a standard SI or metric unit, but it's very relevant to talking about weather and climate because it has that link to our average air pressure. And the amount of pressure could also be described as being about 100 newtons per square meter or about 14 pounds per square inch. So 1 bar is about that much force being exerted on things. So a bar is our standard unit, but you'll usually see air pressure described in millibars. And so that's what's on that map there. You see at the top it says sea level pressure MB for millibars. So just like a millimeter is 1,000th of a meter, a millibar is 1,000th of a bar. And you can actually see that if you look at the actual amounts that are given on that map. These are pretty typical air pressure amounts that you would see on a map like this. And so you'll see most of these numbers are kind of close to 1,000. So 1,000 millibars equals 1 bar is kind of that average pressure there. And so you can see at some of the highest pressure areas on this map, we're getting up into like the 1030s of millibars, and in some of the lowest pressure areas, we're getting down to like the 960s in millibars. So they're staying around that average of 1,000 millibars or 1 bar. And we can measure this air pressure with a barometer. Right? A barometer, our device for measuring air pressure, uses that same the same word bar in there, and that actually comes from a Greek word baros that means weight. So you can think of air pressure as the weight of the air pressing down onto us here at the surface of the Earth. So the weight of that air is the air pressure that it's exerting on us. Air pressure is important because that's what determines wind. So wind is the movement of air from an area of high pressure to an area of low pressure. And so that should kind of make sense, right? Where there's high pressure, there's sort of more air packed into there, and it's going to get squeezed out towards the low pressure areas. Or if you imagine blowing up a balloon. So if you blow up a balloon, you are forcing lots of air into that balloon. It's exerting a lot of pressure. That's what keeps the balloon out and around like it is. But then if you let go of the opening in the balloon, that the high pressure within that balloon is going to want to escape. It's going to want to equalize with the lower pressure of the air around the balloon, and so all the air is going to come out until it's equal levels of pressure. So in the atmosphere, the same thing is happening. The air in places that have high pressure is flowing towards places of low pressure. That's the basic reason that we get wind. So if you're ever outside and you feel the wind, you can point into the wind, and that's the direction of higher pressure. Or if you point along with the wind in the direction the wind is going, you're pointing towards the place that is lower pressure. So that's what's represented in the upper diagram there, right? We've got a high and a low pressure area. Wind is blowing out from the high pressure area and into the low pressure area. But this is all occurring on a spinning globe. And we have talked before about one of the effects of being on a spinning globe is something called the Coriolis effect, right? That causes the paths of things moving across the Earth to appear to deflect to one side or the other. And so you can go back and rewatch the little video illustrating how the Coriolis effect works if you need a little refresher on why it is that things flowing across the surface of the Earth would seem to get deflected to the right in the northern hemisphere, to the left in the southern hemisphere. But that Coriolis effect is going to affect our winds blowing out of high pressure zones into low pressure zones. And so that means rather than coming straight out or straight in, those winds are going to make a spiral pattern. So they'll spiral outward from a high pressure zone, they'll spiral into a low pressure zone. And so here in the northern hemisphere, so all of this on this slide is specific to the northern hemisphere, since that's where we live right now. You would flip it around if we were looking at the southern hemisphere. So as that wind flows out from a high pressure zone and it gets bent to the right as it goes, that's going to create a clockwise spiral. So wind blowing out from the high pressure zone is going to make a clockwise spiral that you can see in the image there. But then it's going to end up making a counterclockwise spiral blowing in towards the low pressure zone. So if you imagine that wind, it's trying to come straight into the low pressure, but it gets deflected off to the side to the right, and so it has to spiral around to get into the low pressure zone instead of being able to blow directly in. That ends up creating a counterclockwise spiral around a low pressure zone. So you will see winds spiraling either clockwise out from a high pressure zone or counterclockwise into a low pressure area here in the northern hemisphere, and then opposite to that in the southern hemisphere, since in the southern hemisphere the Coriolis effect makes things seem to bend to the left. So in terms of where we get these high and low pressure zones, the air that is moving across our Earth tends to be divided into these big blobs, these big air masses that have relatively homogeneous temperature and humidity. So this might be a warm and humid blob of air, it might be a cold and dry blob of air, it might be a cold and wet blob of air. This big sort of semi-continental sized areas of air that have relatively similar temperature and humidity throughout them. And the center of each of these air masses is a high pressure zone. So the center of a big air mass is an area of high pressure, and then low pressure occurs where these air masses come together. So the joints between these air masses are areas of low pressure. And so we're going to see the winds blowing out away from the center of these big air masses and towards the places where they join up. So when you have high pressure, you have generally very consistent and very calm weather. So if the sky is clear and the winds are gentle and things are fairly calm, they might be calm and very cold, calm and very warm, depending on the nature of the air mass that you're in, but then you're in the middle of a high pressure zone. But then you get a lot of change happening at the low pressure zones, because that is where these air masses interact, where you're seeing a change from one air mass to another. And so that's going to involve changes in temperature, changes in humidity, and that's the spot that all of this air is blowing towards. And so then that is where we're going to see a lot of interesting weather happening. And so we describe the connections, the spots where these air masses meet, as fronts. So two air masses meet at a front, and that is going to be a low pressure zone. And these fronts are usually called either cold fronts or warm fronts. And there are a few other ones that we'd get into if this was a meteorology class, but since we only have this one lesson here, we'll focus on the two main kinds of fronts, cold fronts and warm fronts. And the names simply come from the relative temperature of the air mass that is coming up from behind. So these air masses are always moving, and typically in the lower 48 United States here where we live, the prevailing movement, the prevailing direction of air movement is from west to east. So these air masses are kind of moving across the continent from west to east. And so whatever air mass is coming up from behind gives its name to the front, because the front is the front of that second air mass. So if a colder air mass is coming up from behind a warmer air mass, that is a cold front. We're at the front of the cold air mass. And if a warm air mass is coming up from behind a colder one, then that's a warm front, right? We're at the front of that warm air mass. And cold and warm here are relative. So any two air masses are probably going to have at least slightly different temperatures. So whichever one is colder is the cold air mass in this context, and whichever is warmer is the warm air mass. Even though, a cold air mass during the summer is a lot warmer than a warm air mass during the winter. So these are cold and warm are relative to each other at the comparison of the two air masses that are meeting at this front. So these air masses come together, and what ends up happening is that the warm air gets lifted up on top of the cold air. So this isn't a vertical kind of divide. It ends up slanted, with the cold air going underneath and the warm air going up on top. And that's because cold air sinks, warm air rises, right? Basic thing about air temperature: warmer air likes to rise, colder air likes to sink. And so regardless of whether it's a cold front or a warm front, the warmer air is going to end up on top and the colder air is going to end up underneath. Now, we've talked before about what happens when air gets pushed up, right? We discussed this in contexts where air is getting pushed up by, for example, going across a mountain range, right? And we said when air gets pushed up, it cools off. When it cools off, its capacity to hold moisture is going to decrease, right? Colder air can't hold as much moisture. So its capacity to hold moisture is going to decrease. And so that means the relative humidity is going to increase because it's got some amount of water vapor in that air. And so eventually that the amount of water vapor that the air can hold is going to shrink and shrink until it's the same as the amount of water vapor that the air actually has in it. And then if it continues to cool off, then some of that water vapor is going to be forced to condense. It can't remain as water vapor. It's going to have to become a liquid form. It's going to have to condense out of that air. And so we're going to get the formation of clouds. And then those clouds are going to result in precipitation. So that basic sequence that we talked about when we were looking at how air moves across a mountain range also happens when air gets pushed up by the action of a front. So simply the meeting of a colder and warmer air mass will push that warmer air mass up and lead to condensation and then precipitation. So if you're getting precipitation, you are probably experiencing a front moving through. And you may have noticed that it often happens that you can really tell a difference in temperature before and after rain has come through. So it might have been really cold, and then we get some rain, and then afterwards it's now warmer, or vice versa. Right? It was really warm, and we got some rain, and now it's colder. So the difference in temperature that you're feeling before and after that rain is an indication that that a front has come through, that you were in one air mass with one temperature, and then the front passed over, and now you're in a different air mass with a different temperature in it. So both cold and warm fronts create precipitation. Typically, cold fronts create more intense winds and precipitation because cold fronts tend to be steeper. So as the cold front, the cold air pushes the warm air up at a cold front, it tends to create a steeper situation, and so it creates generally more intense precipitation, whereas warm fronts tend to be gentler as the warm air slides up over, and so you get gentler, although sometimes lasting for longer kinds of precipitation. Although those differences are kind of broadly on average, it's not a sharp divide, because again, both types of fronts will produce precipitation. So if we put this all together, we get a formation that we call a mid-latitude cyclone. So this is what lies at the base of most of the storms that we would experience here in the lower 48 United States. As our typical storm formation is this mid-latitude cyclone. So what we're seeing here, this map gives you a kind of idealized version of a mid-latitude cyclone. So we've got some cold air masses to the north, and we've got a warm air mass to the south, and the spot where the warm and cold air masses meet is marked out by these fronts. And so we've got a low pressure zone there at the juncture between our air masses, which means that the air is spiraling in towards that low pressure zone in a counterclockwise direction. And you can see that with all the little flags there. Those are a way of symbolizing the speed and direction of wind. We're not going to get into exactly how to read one of these traditional weather maps here for this class, but if you kind of imagine each of those as like a ball and it's got this tail, right, and the tail is streaming behind it, so you can see that counterclockwise motion of those winds. And so that's going to twist the fronts around, and you get this kind of shark fin shape where you've got your cold air mass around the top, and then your warmer air mass is kind of poking up into the center of it in that kind of shark fin kind of shape. And so at the front edge of that, you've got your warm front, right, because that's where the warm air, which is moving eastward across the country, that's the front of that warm air mass, where it is encountering and then sliding up onto the cold air mass. And then you've got the cold front there, represented in the blue with the little triangles, where the cold air mass is coming up from behind the warm air mass, right? So again, everything moving eastward, so the cold air mass coming around from the east, meeting the warm air mass and kind of nosing under it, and that creates the cold front there. So our storm system, we've got that low pressure zone with the warm and cold fronts extending out from it, and then all the areas in gray that you see on this map are areas of precipitation. So we've got precipitation around the center of the low pressure zone and then out along both of those fronts. So that is where the warm air is riding up on top of the cold air, and that causes cooling of that air, which causes increased relative humidity, eventually leading to condensation, and then the condensation can fall as precipitation. So that is the basic anatomy of the storm systems that we typically get here in Pennsylvania and throughout the rest of the lower 48. So often, and especially along the cold fronts, where we have sort of more intense storm activity, you also get precipitation accompanied with thunder and lightning. And so thunder and lightning are both essentially the same thing. We're just talking about, are we seeing it or are we hearing it? And that's the difference between thunder and lightning is it the light or the sound that we are detecting? So we get thunder and lightning when we get rapidly rising air. So we've got, say, a cold front coming through and it's pushing that air up very rapidly, and all of the little ice particles in that air as it rises. So it's started to have condensation. That condensation has frozen, and those ice particles are rubbing past each other as they are driven upward into the air, and that's going to build up static electricity. And so it's kind of the same thing as the way you get static electricity if you rub a balloon on your hair or if you scuff your feet across the carpet, right? By rubbing things together, you're knocking electrons off some of them and onto others, and so that's creating differences in the electrical charge. So you're building up static electricity by this rapidly rising air with ice particles in it. And if you start to get a significant difference in electric charge between either two parts of the clouds, so you got one part of the cloud that's negatively charged and one part that's positively charged, or a difference between the charge of the clouds and the ground, so maybe the cloud is negatively charged and the ground is positively charged, and you get this difference in the electrical charge, then that is eventually going to get neutralized, right? Because big differences in electrical charge aren't stable. So there's going to be a release of electric energy to neutralize that difference in electrical charge. And that is what produces the thunder and lightning. So we can see that release of electrical charge in the form of a lightning bolt, and we can hear the vibrations that it causes in the air in the form of thunder. And so the lightning and thunder are produced at the exact same time, right? The thunder is just the sound of that lightning bolt. But because sound is a mechanical wave, right? It's moving through the air, and the light that we see from it is an electromagnetic wave that's moving at the speed of light. The light's going to travel faster than the sound. And so if you are some distance away from this event, there's going to be a lag time. You're going to see the lightning before you hear the thunder associated with it. And there's a little rule of thumb that you can use if you're trying to estimate how far away a storm is. If you see some lightning and then count the number of seconds until you hear the thunder. And if you take the number of seconds between seeing the lightning flash and hearing the thunder and divide it by 5, that gives you roughly how many miles away that was happening. So if it's 5 seconds of a gap, it's a mile away, etc. So you can estimate just based on the difference in the amount of time that it takes for the light and the sound to reach you, how far away you are from this event. Okay, so before we get into talking about some of our storms with serious amounts of precipitation, I want to say a little bit about storms that don't have precipitation, because you can get storm activity in a context where the air is so dry that you're not getting any significant amount of precipitation, right? Because if the air doesn't have any moisture in it, you can't cool it off enough to cause condensation. There's just nothing there to condense and to eventually fall as precipitation. So in very dry conditions, you get storms without any associated precipitation. But these can still carry a lot of hazards with them. So if there is thunder and lightning, then we've got dry lightning. So dry lightning is lightning that's not accompanied by precipitation. That is a common cause of wildfires. So wildfires that are started by lightning are usually happen in a context where there's not a lot of precipitation, because of course that precipitation would put out a fire that the lightning started if the lightning was accompanied by a lot of rain. So it's a major cause of wildfires, especially in the western part of the United States, where dry lightning is much more common than here in the east, where our atmosphere is usually moist enough that we tend not to get a lot of lightning that's not accompanied by precipitation out here. Another thing that can happen if you've got a storm, it's accompanied with a lot of wind, and if you are in an area with limited vegetation cover, so you're in a place like a desert, like in the southwest of the United States, then those winds can pick up a whole lot of dust off the ground. So if you don't have plants holding that soil in place, it can get blown up into the air as dust, and then you get a dust storm. And that carries with it a bunch of hazardous effects. So all of the small particles of dust can be really dangerous to breathe. So very small particles get taken very deeply into your lungs and can cause a lot of problems. So it is a bad idea to be breathing in the air in a dust storm. You should really use some sort of a mask or a respirator, break out your old COVID masks if you're caught in a dust storm, so that you're not breathing those tiny particles deep into your lungs. There's also a danger that it might be more than just dust. There might be other dangerous things in that dust. So there may be pollutants. So if the storm is blowing across an area where there is pollution in the soil, then that pollution is going to get picked up, and you're going to breathe that in with the dust. It can also pick up harmful disease agents, and so the one that I've noted on the slide there is fungal spores that cause a disease called valley fever. And so this is a serious disease that you can catch in the southwestern United States. So in places like Southern California or Arizona, this is a fungus that lives in the soil in those areas. And so if the dirt gets blown up into the air in a dust storm, then the spores from that fungus, you can breathe them in, and for some people that will cause a really life-threatening disease that we call valley fever. And there's not really even a good treatment for it besides just addressing the symptoms and hoping that people recover. So it's becoming an increasingly serious issue in that part of the world. And it's made worse when you have activities that are disrupting the soil. So if you have, for example, construction, and construction, you're driving bulldozers around and digging holes and all that kind of stuff, that's breaking up the soil. That makes that easier for that soil to get picked up in a dust storm, and so then that makes the dust storm worse, and it makes it more likely if there are valley fever spores in that dirt that that'll get blown around and somebody will breathe that in and and come down with a disease like valley fever. So dust storms can be very dangerous to get caught in. The picture there that I've shown you is maybe similar ones that you've seen where the dust storm is visible as this like giant wall of dust coming across the landscape. And when we see this kind of huge dust storm created by the passage of a front, the technical name for this kind of storm is a haboob. So this comes from an Arabic word meaning to blow, and it's been adopted as kind of the universal name for this kind of storm. And it's a fairly recent, like the last few decades development, that the word haboob has become more popularized. I was actually living in Arizona in the mid-2000s when the word haboob started to be used much more often. And of course, you get a lot of haboobs in Arizona. And that was also the time period shortly after 9/11, where there was a lot of really irrational prejudice against anything that had to do with the Arabic language or Arabic culture. So there were a lot of people freaking out about this term haboob because like, why are we calling our storms this Arabic word? And it was, in my opinion, kind of silly. Because it's just a word that means to blow, and there are a lot of these kind of storms in Arabia. So the Arabic language got to name this storm type and use the same word in America so that we're clear that we're talking about the same kind of storm. Okay, so some storms don't come with precipitation, but certainly the ones that we get here in Pennsylvania almost always have quite a bit of precipitation with them. And there's a bunch of different types of precipitation depending on the temperatures that the water is encountering from the point of condensation through to when it hits the ground. So most clouds in the mid-latitudes here are cold enough, right? You're at that high elevation, the air has been cooling as it rises, and that's what's causing the condensation. They're cold enough up there that this condensation freezes into ice crystals. So the composition of a cloud that you would see here in Pennsylvania usually is mostly made up of ice crystals rather than droplets of liquid water. So a precipitation will start off as ice crystals, and if it remains in that form the whole way down to landing on the ground, then we're dealing with snow. So snow is that precipitation that's falling in the form of ice crystals that are hooked together with this six-sided symmetry. So when water freezes, it forms hexagonal crystals, and so you end up with this six-sided symmetry as a bunch of tiny little ice crystals connect to each other and create a snowflake. So snow is in some sense the simplest form of precipitation because you've got ice crystals in the cloud, they fall to the ground, you've got snow, there you go. Rain usually actually starts as snow when it's just falling out of the clouds. It's usually essentially snow at that height. But then as it falls through warmer air closer to the ground, it melts. and so a melted snowflake becomes a raindrop. So it's melted into liquid form by the time it hits the ground. So rain is melted snow essentially as it falls. We also have freezing rain. So that precipitation, starts as snow, melts into rain on the way down, hits the ground, but then if the ground is cold enough, so you've got perhaps, we've got warm air that has melted the rain, but then the ground itself is really cold, then that can refreeze that water. So it hits the ground, or it hits, trees, or it hits telephone wires, or buildings, or cars, or whatever. If they're cold, it will freeze back on. And when it freezes, it's going to form solid sheet of ice. It's not going to, create the airy, fluffy little crystals that it was back when it started out as snow. It's going to freeze into a solid layer. So that's freezing rain, is rain that it has melted as it fell, but then it refreezes when it hits things on the ground because they are extremely cold. And of course, freezing rain is one of the most dangerous types of precipitation because you get that little layer of ice on the ground that makes walking or driving very dangerous and difficult to keep yourself upright and going where you want to go. And then also having this layer of ice attached to infrastructure can cause tree branches to break off, it cause telephone lines and power lines to come down, and so forth. So it can be pretty dangerous when that happens, but it's simply happening because the ground is super cold and is freezing that rain as it lands. If the rain refreezes before it hits the ground, so it starts as snow, it melts into rain, but then it hits cold air just before it gets to the ground and refreezes, then you get sleet. And so sleet is basically frozen raindrops. So again, because you've got this blob of water and it just refreezes as one blob, you get the little pellets of ice rather than fluffy snowflakes that form as tiny crystals of ice come together. So instead you get the sort of pellet-like form of ice. So sleet is basically just frozen rain that has frozen before it hits the ground. And if you're listening to the weather report, you may hear them talk about a wintry mix. That's not really a technical term, but it basically means you've got a mix of rain, snow, and sleet. So you've got conditions that are kind of right on the edge between each of those different forms of precipitation, and over time or from one place to the next, over a short area, you might get different ones happening. And so, they describe it as just this wintry mix. It's all of these things might be happening. Then the last type of precipitation to note is hail. So hail is also balls of ice, but it's a little different from sleet because hail is formed when you have freezing precipitation that's held aloft by strong winds. So rather than just simply falling to the ground, you have updrafts of winds that are strong enough to keep bouncing these chunks of ice back up into the air where more ice freezes onto them. And the stronger these updrafts are, the bigger a thing they can keep up there before it gets big enough and heavy enough that it's going to fall. And so the bigger the hailstones that you're going to get. So if you have really strong updrafts in your storm, air rising very rapidly, it can basically keep tossing these balls of ice up to get more ice frozen onto them, and that will result in the formation of hailstones. Hailstones, of course, being also a very dangerous form of precipitation because by the time they're big enough to fall, they have a good bit of mass and they're accelerating from high up in the clouds, and so they can do a lot of damage when they hit things. They can, of course, damage things like cars, crack windshields, and so forth. They can hit people and injure you. Hail also does a lot of damage to crops. It's a common cause of the loss of crops on a farm. If you get a hailstorm that comes through, those hailstones are big enough to knock down corn, and then if your corn all gets knocked down by the hail, then it's not going to grow and you're not going to have any corn. And likewise for other crops. So hailstorms can be very destructive when they come through. So a type of storm that we're pretty familiar with here in the northern part of the United States is a blizzard. So a blizzard is simply a severe snowstorm. So it's a storm with snow that is really bad. And the National Weather Service puts the technical dividing line for a blizzard based on the wind speed and the loss of visibility. So you have wind speeds of 56 kilometers per hour, which is 35 miles an hour or more, and you have reduced visibility. So you've got snow and it's blowing around so much that you can't really see very far ahead of you. And so the technical dividing line is 400 meters or a quarter mile of visibility. So if you have that much or less visibility for an extended period of time, then that qualifies you as a blizzard. So it's not really about the volume of snow. So a blizzard may not have any more total snow falling than a non-blizzard snowstorm, but it has these very strong winds, and so those winds are blowing that snow around. Right? That's since snow is frozen, but also very fragmented. It can blow around in the air a lot more than other kinds of precipitation, and so it creates those whiteout conditions where you can't see very far ahead of you. And so that's what defines something as a blizzard. And the word blizzard actually comes from the same Old English root as the word to blow. So in a sense, a blizzard and a haboob are etymologically kind of the same thing. They're both instances of blowing. It's just that they got blowing dust in Arabia and blowing snow in England, and so we get the words haboob and blizzard applying to different kinds of storms depending on what's blowing around in that storm. So, in terms of the dangers presented by a blizzard, so one of the main things is that the snow and wind can cut off transportation. So if you have your roads covered in snow, you've got high winds that make it dangerous to drive. The combination of snow and wind can create drifting, which means that even if the total amount of snow isn't huge, if the winds are blowing that snow all into one place, then that can create a lot of complications, because now we've got a snowdrift blocking things, and the snow will usually accumulate against things like hillsides and walls and so forth, or in low points, and so it may create more of a hazard and more of a complication for transportation than it would if it just all fell evenly with relatively little wind. You've also got damages to infrastructure from cold. So a blizzard often accompanied by extreme cold, and so that can do damage to infrastructure, like causing pipes to burst when the water in them freezes. Blizzards can also knock out power. So if you've got power lines and they're being subjected to a whole lot of wind and getting battered by the snow being blown around, knocks out the power, then that's bad in and of itself, and that can lead to cascading complications. So if the power to your house goes out and your furnace turns off, and then your pipes freeze, so one disaster can follow from another. There's also a risk from heart attacks from people who are trying to shovel out that snow. So if you're trying to dig yourself out, and that's actually a surprisingly common cause of medical problems and even deaths during a major snowstorm, is actually not from the direct impact of getting caught in the snow and freezing or something like that, but from people who go out to try to remove the snow, try to shovel out their car or shovel off their driveway, and that exertion, because it's a lot of work, especially if the snow is relatively wet. It's a lot of work to shovel that snow. That can trigger something like a heart attack. So there's a bunch of different hazards that are presented by a blizzard, but it's important to remember that the severity of the impact depends a lot on people's experience with blizzards and their preparedness level of the community. So you see very different impacts in different places from the same size of a blizzard event. So this should bring back our discussion of vulnerability. Right? That a disaster is a combination of the hazard event, like the blizzard, and the vulnerability of people exposed to it. And so a good illustration of how this works out is if you contrast the way that blizzards get dealt with in a place like Buffalo, New York, that sees major snow every year, and Washington, D.C., which is kind of on the borderline, that they don't get blizzards very often, but they do get them sometimes. So the DC is in this kind of area where people are often not very prepared for a blizzard because they don't happen super often. They don't have a lot of experience dealing with them. And so even a relatively small blizzard, something that people in Buffalo might just shrug off because they get worse than that every month up there, might become a major issue and snarl traffic and shut down the city practically for days. And so my illustration there, I've got one meme that I grabbed from a Buffalo page. Buffalo be like, it ain't that deep, and this guy's just wading through waist deep snow because they're used to it. It's no big deal. They're prepared for it. They know how to deal with it. And then the lower image comes from a Washington D.C. page where they're kind of poking fun at the kind of panic that people in DC might go into when there's a hint of a possible blizzard because they don't know what to do. They're not prepared for it. And so, the little girl's going out to the store for bread and milk after seeing one snowflake. So the difference in preparedness levels between different places can create big differences in the vulnerability of those places to a storm, even if the size of the storm itself, the amount of snow and the strength of the winds and stuff aren't that different. So moving from blizzards to hurricanes. And we've talked a little bit about hurricanes before in an earlier lesson. So you have the basic concept of a hurricane, but I want to talk a little bit more about it in the context of talking about storms and show how some of the things we've been saying about storms apply to hurricanes as well. So the storms we've been talking about before were in that category of mid-latitude cyclones, right? So a typical storm hitting the lower 48 United States would be a mid-latitude cyclone because we're in the mid-latitudes. A hurricane, on the other hand, is a tropical cyclone. So it's the same general category of storm in the sense that it is a low-pressure area. You can see the winds spiraling counterclockwise into the center in the northern hemisphere. The picture there is a hurricane in the Gulf of Mexico. So you can see the wind spiraling into the center in that counterclockwise fashion. So in that sense, it's very similar to the way a storm system in the mid-latitude cyclone category would work. It's just that it originates in the tropics. So it's a tropical cyclone. And so the terminology varies a bit in different parts of the world. So I'm going to be saying hurricanes because that's what we call them in the Americas. So when we get this type of storm in the Americas, we call it a hurricane from the name of the Mayan storm god Huracan. In East Asia, so China and Japan, they refer to this exact same kind of storm as a typhoon. And in Australia, Africa, Indian Ocean area, they just call them cyclones. But again, it's the same kind of storm. In those areas, it's going to be rotating the opposite way because they're in the southern hemisphere. But it's essentially the same kind of storm. It's just a different name in different parts of the world. And as we've said before, hurricanes pick up their energy from the evaporation of water over warm ocean. So you've got this warm ocean water. As the water evaporates, it's sucking up energy from the water. And then as the water condenses back into the clouds, once it gets aloft, then it's releasing that energy. And that release of energy is what powers the storm, what creates the high-speed winds that define a hurricane. So we've been mentioning, this counterclockwise spiral in the northern hemisphere of the winds in a hurricane. The winds are spiraling in towards the center, but at the very center of the hurricane is something called the eye. You can see it pretty clearly in the illustration there. There's the little point in the middle, and you can see the clouds are kind of breaking up in the middle. So the eye of the hurricane is this calm zone at the center of the hurricane, this little space of calm. And so people that have lived through hurricanes where the eye has passed over them have described this really kind of freaky experience that you've got these really intense winds and huge amounts of rain hitting you as you pass through the hurricane, and then the eye hits and just it clears up. The sun comes out because there's no clouds, and the winds die down for a brief moment of time as the eye passes you, and then you get back into the rest of the hurricane, and the winds and the rain and everything pick back up. And the part of the hurricane immediately around the eye, so you've got the eye that's this calm zone right at the center of the hurricane, but the area immediately around the eye that we call the eye wall is the most intense part of the hurricane. It has the strongest wind, usually has a lot of thunderstorms going on there, so you're getting thunder and lightning, and lots of rain, strong winds right around the eye. So it's this kind of paradox that the very center of the hurricane is this little calm oasis, but immediately around it is the eye wall with the most destructive part of the hurricane, the biggest and strongest winds and rain there. So what you're seeing now is a typical hurricane forecast that might show up on the news or something if a hurricane is approaching. And it's important to note what this is actually showing. So you can see that we've got the current location of our hurricane. We got labeled there 10 a.m. Tuesday, so that was when this particular diagram was made, was when there's a hurricane in the Gulf of Mexico at 10 a.m. on a Tuesday. And then you can see this kind of cone spreading out from there. And this particular hurricane is being predicted to kind of loop around, hit the coast of Texas, and then cross back over into the northeastern United States. So it makes this kind of cone-shaped area that is the prediction. And I've got kind of the rough times they expect it to hit there. What this cone is showing you is the range of possible paths for the eye of the hurricane. So if you look at the beginning of that cone, the point of it is at the current location of the eye. So we know exactly where the eye is now, so that's a point. And then we know roughly the trajectory that's going to take. And we can predict from our weather models that this hurricane is going to loop up northwards, make landfall, and cross back across the United States there. So we know the general trajectory, but we don't know exactly. Right? It might veer a little farther southward. It might veer a little farther northward. So you can think of the outer edges of that cone as the farthest out paths that we predict that the eye of the hurricane might take. So that means if the eye of that hurricane is taking, let's say, the northern edge of that cone, right? So it's coming around kind of the outside and across the northern edge as it goes back across the United States there. If the eye is following that edge of the cone, the hurricane itself is going to be much, much wider, right? You can see the orange blob there around the beginning of that cone, right? That's the extent of the current hurricane. So if you imagine a blob that size coming around the outer edge of that cone, so it's spreading out past the edge of that cone. So areas along Lake Erie, for example, would get hit by the hurricane as it comes around if it were to follow that farthest kind of west and then north side of the cone. So what we're seeing there is range of possible paths of the eye, and then the storm as a whole would spread out significantly to either side of that. So a lot of people will interpret this as this is the area that's going to be affected by the hurricane. But in fact, the hurricane is going to potentially affect people off to either side of it, depending on exactly what trajectory the eye follows. All right, so we've talked about several different kinds of storms. What can we do about them? Well, the main thing you can do is be prepared, because there is no way for us to stop or steer a storm. There have been some experiments. People have had ideas about cloud seeding and stuff to try to get a storm to blow itself out before it hits something, or to try to adjust its trajectory. None of that has been effective. So we have no way of steering or stopping or reducing the impact, reducing the strength of a storm. But what we can do is be prepared for it so that we are not harmed as much by it. Right? We can lower our vulnerability to the storm so that it's less of a disaster, even if the hazard event we can't do anything about. And we can do that at the individual level and kind of collectively at the community level. So at the individual level, things you can do: follow weather reports and warnings. So pay attention to the weather, pay particular attention if they're predicting a potential storm. Pay close attention to how big of a storm is being predicted, what kind of a storm, when it's going to happen, etc. And then during the storm, again, keep up with it so that you're aware of what's going on and can make well-informed choices. You can have supplies on hand in advance. So that meme a few slides ago was kind of making fun of the way that people will, in a panic, rush to the store and buy bread and milk and perishable staples like that right before a storm rolls in. But there's a lot you can do in advance to have a good supply of food on hand if storms might be coming through, to have batteries for devices in case the power goes out for an extended period of time, to have medicines and medical equipment in good working order, and have your supply of what you need in case you can't get to the pharmacy, or something happens like the power goes out so you can't power a medical device you need. You have a backup, a way to power it. Having all that squared away in advance will make things go a lot easier for you. Don't travel unnecessarily during a storm. So sometimes you need to travel, sometimes it can't be avoided leaving your house, but if you can avoid it, don't go out. Because every car on the road is another car that could get into an accident, that could slide off the road into a snowbank, or get washed away as a flood comes through a low-lying area, or whatever might happen. If you're out there on foot, again, you're another person that could end up having some sort of issue, and then you're in trouble, and then that also takes up emergency responders' time to come save you. So don't travel unnecessarily during a storm. Know where to go if your home becomes unsafe. So have a backup. If you lose power at your home and it gets, for example, too cold during a blizzard for you to be able to safely stay there, do you have somewhere else that you could go to? That would be a case of necessary travel, right? Someplace else you can get to. And check in on neighbors and family, especially if you have people in your life who are elderly or disabled or in some other way might need extra help dealing with the storm. Check in on them, make sure they're doing good, see if they, you can shovel their walk for them, and then they're not risking a heart attack doing it themselves, etc. Then on a collective or community level, there are things you can do like pre-deploying supplies and equipment. So if we know a blizzard is rolling in, for example, communities can position snowplows and supplies of things like road salt in the right places to be able to get out and clear the roads quickly as the storm comes through. You can build more resilient infrastructure. So when we're building things like bridges and roads and buildings, they're built to withstand a certain amount of force from wind and rain and so forth. And so by making good judgments about those things and building in safety margins on how we build those things, even if it costs a little more upfront, can really help both to avoid those things being damaged and having to be replaced, but then also avoid the problems that might be caused if the bridge collapses in the middle of the storm and now people can't get where they need to go, you can't get needed aid in, etc. You can coordinate relief efforts through trusted institutions. So having a good way to get help to people after a storm has come through is a very important thing and can make a big difference to how well people weather that storm. If there are trusted institutions in the community, things like religious institutions, community centers, etc., that can coordinate that know the people, that know what people need, that people are going to trust to go to for help. And then if there's aid available, applying for it easy and accessible. So there are a lot of times when people get caught up in some sort of disaster, and there's aid that might be available to them, whether that's an insurance payment or aid from the state or national government or from a private charity or something. There's aid that they could access, but they get blocked by, for example, the burden of paperwork that's too complicated, or that has to be submitted in certain formats that they don't have access to, right? If you're out of power, you can't print anything from your computer. So needing to print things on your own isn't gonna work in a scenario like that. Or something like the language that the application is in. So if you have a community that has lots of people whose first language is not English, then if all your forms are in English, those people aren't going to be able to access it, and so they're going to suffer worse impacts from the storm, or a lot of these comply to any sort of hazard event. Okay, so now let's talk about tornadoes. So I'm putting tornadoes separate because they're a bit of a unique scenario. a little different from other kinds of storms. So a tornado is a rotating column of air connecting the ground to the clouds. So you can see in the picture there, we've got this narrow rotating column of air in the classic funnel cloud shape, and one end of it is hitting the ground, the other end of it is connected up to a big thundercloud. So tornadoes are always associated with thunderstorms and with the giant clouds from which thunderstorms come. And what you're seeing there, what's visible, that funnel cloud is full of condensation. That's what you're seeing there is condensation that's occurring. So it is literally a cloud there in the center of the tornado. Depending on what kind of surface the tornado is passing over, there may also be water in there, so you get a water spout if your tornado is passing over a body of water, or there may be a whole bunch of dust in there if it's passing over an area that has, a lot of loose soil, and so it's pulling up dust, and then you're getting a dust storm tornado. And a tornado is kind of distinctive because it's so narrow. So a blizzard or a hurricane is going to affect a gigantic area as it passes over, but a tornado, the spot that contacts the ground in a tornado, is usually only a few hundred meters wide. So it's very small compared to the size of other kinds of storms, and it will usually travel along the ground for less than 10 kilometers. There are some tornadoes that last longer than that, but typically a tornado won't make it more than 10 kilometers before it starts to break up, it loses contact with the ground, and it ceases to be so destructive. So you have a relatively short path that the tornado goes through. So it does an enormous amount of damage to the areas it hits, but it's hitting this narrow, short pathway as it goes through. On the other hand, tornadoes often come in clusters, because if you have the conditions for tornadoes to form, it quite often will make more than one. And so you have several tornadoes coming through, slightly spaced out. So that does increase the amount of destruction that gets done in a tornado event. And another interesting thing about tornadoes is that they're more common in the United States than anywhere else on Earth. So particularly in the Great Plains, we just have the perfect recipe of conditions for tornadoes to form easily. So they can be found in other parts of the world, but they are far more common here in the US than anywhere else in the world. And while they're more common in the Great Plains, we can get them other places in the United States as well. And so one of the supplementary things that I'm going to have you look at is a video about a group of tornadoes that came through Western Pennsylvania back in 1986. So it was a very major tornado event and happening in an area that we don't get tornadoes that often in here in Pennsylvania, but they do occur and they can do a lot of damage. And sorry, it was 1985, not 1986. And that particular tornado event stands out to me because I was living in Pennsylvania at the time. I was living up in the little town of Tynesta in Forest County. Some of you may be familiar with it if you've been to that part of the state. And I was 5 years old at the time, and my house was kind of out in the countryside, a little ways away from the town itself. And my dad worked in town, and the tornado came through right at the end of the day. So my dad was getting ready to come home from work, and the tornado went through, and it blew down all the phone lines. So my mom was really worried. She was at home with us kids because she couldn't get in touch with my dad days before cell phones. So if the landline went out, you couldn't get in touch with people. So the phones were out. She couldn't get in touch with him. She didn't quite know what had happened. Luckily, the tornado had come through. It came right across the road between the town and our house, but it came through before my dad was driving there, so he didn't get caught in the tornado. And he also, luckily, had a chainsaw in the back of his pickup truck, and so he was able to cut away a bunch of trees that had gotten blown down over the road that would have otherwise blocked him from getting home. So he was able to help clear the road and get through and home, and we were very glad that he made it home safely. And what I mostly remember from that day, because I was far enough away that I wasn't able to see the funnel cloud, so I didn't see the tornado itself. But as you can see from the photo there, the tornado is associated with a thunderstorm, much bigger thunder cloud around the tornado. And so there was a whole lot of hail falling at my house. So I remember sitting on the porch watching gigantic, like some of the biggest hailstones I've ever seen, falling around our house while the tornado went through, across the road between us and town. And for the rest of the time that we lived there, we could see exactly where the tornado had gone through, because it took a very long time for all of the trees that got knocked down by that tornado to fully regrow. And you can't really see it anymore today because it's been 40 years since that tornado. But at the time, it was really obvious. It left this kind of scar across the landscape where that tornado had come through. Okay, so how do tornadoes form? How do we get this, weird kind of weather phenomenon? So as I said, they are associated with thunderstorms, generally along a cold front. And so they're accompanied by thunder and hail, and that's what I was seeing when I was a kid at my house. And the way that the tornado gets going is that you have wind shear. So this is a difference in wind speeds between the wind that's blowing at the ground level and the wind that's blowing farther up in the atmosphere. So you get faster winds aloft and weaker winds at the surface. And by having those different wind speeds, that causes the air to spin. So it's kind of like, if you've got a wheel and you push it one direction at one side and the other direction at the other side, you make it spin. So having these different speeds of winds going along makes the air in between them spin. So it actually starts as a horizontal spinning air. So horizontal air being spun by the difference in wind speed. But then the updrafts in the thunderstorm, so the rising air that is coming up into the thunderstorm and causing the condensation that's going to result in the thunderstorm, that the updraft, that rising air, then takes this bundle of rotating air and tilts it upward. So it takes this horizontal air and it turns it on its side, and then once it's vertical, then you're getting that vertical spinning air that forms your classic tornado funnel cloud shape. So tornado actually starts off as horizontal spinning air and then gets turned on its side to create the vertical formation that we recognize. So in terms of safety from tornadoes, there are a few things that are distinct from what we'd see with other kinds of storms and other things that are similar. So you'll sometimes hear on the weather about tornado watches and tornado warnings. And we get similar language used about other types of storms as well, blizzard watch or blizzard warning. And this little taco meme here, I think, really illustrates the difference pretty well. When you hear about a tornado watch, it means you have the ingredients for tornadoes to form. You have the right kinds of thunderstorms that can produce tornadoes. So that's like the taco watch is all the ingredients, the tortillas and the peppers and the lettuce and the ground beef and so forth. A tornado warning is issued when a tornado has actually been spotted. So the taco warning, we have tacos. All the ingredients have been put together. There are now tacos available to be eaten. Tornado warning, we've actually seen a tornado. We've seen that spinning funnel cloud. And so, there's a tornado that is actually out there. So tornado watch is keep an eye out for a tornado forming. Tornado warning is we've got a tornado, and so anybody in its path needs to take shelter, because that's the main thing that you can do when a tornado is bearing down on you, is seek shelter. So ideally, this is going to be in a room that is extremely stable, that is not going to get smashed apart by the hurricane. So basements are good options. My great-grandmother actually survived the tornadoes that I was mentioning before back in 1985 by going into her basement. Her whole house got blown away from her, but she was safe in her basement. So getting into a basement is good, or if you don't have a basement, you can get to an interior room so you're away from external windows, and you would want to sit near the wall so that you have some protection on one side from anything that might get dislodged and fall down on you, and cover your head and neck. And you may have done drills like that in school, right? Put your hands over the back of your neck to protect you. And you don't have to stay there very long because the tornado is going to pass through, and once it's passed, then you can come out of that position. Tornadoes move relatively fast there. That's really the main thing that you can do if there's a tornado. If you are not in a building, if you are out and about, if you can get to a good building, fast, do that. Don't stay in a vehicle. So if you're in a car and you can't drive that car fast enough to a secure, sheltered building, your best bet is to get out of the car and find a low-lying place to hunker down in to protect yourself, because you don't want to be in a car that gets picked up by the tornado and blown around. You are unlikely to survive that kind of a scenario. Another important thing to do in the context of a tornado or any other kind of storm is to beware of scams afterwards. So there's a lot of disreputable people out there that want to take advantage of people who've been the victims of a disaster and try to scam you out of money, scam you out of property, get you to sell them your property real cheap so that you get money quick, or they'll offer to do various kinds of cleanup and repair work for you that they either don't do, they just take your money and run, or they do a poor job of it and you end up having to pay someone else to fix it later. So these people like to prey on victims of disasters, and they usually get out there right after a disaster, and they can be really slick and high pressure tactics. So just be careful if you are caught in a disaster like this about the possibility of scammers. Check people's backgrounds. If somebody is offering to do cleanup work for you or repair work for you, make sure they are a legitimate, reputable person or company, that they have a good track record, so that you don't get an additional disaster on top of the storm disaster. Then you get the disaster of falling victim to a scam. All right, so then the last thing that I want to talk about is the role of climate change in all of this, because these are atmospheric phenomena that we're talking about, so we would expect that climate change would have some impact on them, and in fact it does. So one of the major things that climate change will do is make storms stronger. So we've got the fact that warmer air can hold more moisture. So you can get more precipitation occurring from storms in a warmer climate. Warmer air also means you're going to have more evaporation. And we've talked about how that evaporation is what powers the storms. The evaporation of that water sucks up energy that then is released into the storm and powers the winds of that storm. So a warming world, we would expect to have stronger storms. And we can see that in the graph there if we're looking at the number of Category 4 and 5 hurricanes in the Atlantic region. So we had looked at some graphs about hurricanes before. We had said that the total number of hurricanes hasn't been increasing. We still have the same average number of hurricanes per year. But we had seen that the hurricane strength is getting greater. So the hurricanes that we do get are stronger. And so that means the hurricanes are going to fall more often into the higher categories on the Saffir-Simpson scale. And so what we're seeing here in this graph is the number of hurricanes that get to Category 4 or 5, the two highest categories. And you can see, so this is data from 1980 through 2024, and you can see there is clearly an upward trend there. So the hurricanes that we get are more often these very strong hurricanes that are doing a lot more damage. That is consistent with what we'd expect as a result of climate change. Now, on the other hand, warming is going to lead to fewer blizzards, because to be a blizzard, it needs to involve snow. And so in a warming world, less snow, less often going to be cold enough to have snow. And so blizzards get turned into just regular rainstorms, which tend to be a little less destructive. You don't have, for example, the risk of the whiteout conditions if you're getting rain, and you don't have some of the complications from freezing temperatures associated with the storm if the temperatures aren't freezing anymore. So that is one hazard that we can definitely see being decreased by climate change, is the risk specifically of blizzards. Another thing that climate change can cause is for storms to be affecting unexpected areas. So as our climate shifts, that means the areas typically affected by certain types of storms might shift. And so people that were in areas that they thought they were safe from a certain type of storm might get affected by it. And we saw a good example of that recently with Hurricane Helene in southern Appalachia. So a lot of people had been going on the assumption that hurricanes are mostly a coastal phenomenon, that you have to worry about a hurricane if you're in Florida or Louisiana or on the coasts of the Carolinas. But if you are up in the mountains of the Carolinas or Tennessee or something like that, then you're safe. You're not going to get a hurricane up there. And so we had this hurricane that came through in a very unexpected area, an area that very rarely gets hurricanes, and it caused a lot more damage than it would have if it hit places that were better prepared, where people are used to getting hurricanes. Another effect that climate change can lead to is erosion. So if we've got stronger storms, so we've got an increased volume and intensity of precipitation. So we're talking about just more water falling during our storms, and that water also falling more intensely, so hitting the ground with more force, because the force with which water droplets hit the ground affects how much erosion they're going to cause, how much they are going to dislodge things from the soil that they're hitting if they're hitting harder. So if we have an increased amount of rain, increased intensity of that rain, we're going to get more erosion. We're going to get more stuff washed away by these storms, more landslides triggered by soil getting saturated with all of this rain. And that's especially a risk in areas with lots of steep slopes. So that is actually one of the major risks faced in a place like the city of Pittsburgh. Pittsburgh is built on a whole lot of hills. This picture actually comes from the city of Pittsburgh, where a major rainstorm caused all of that soil under the street there to get waterlogged. It slid out of place. The street collapsed, and you can see they've put up a fencing to keep people from driving there. Although I feel like that one's kind of obvious that you wouldn't want to drive there. But that's an increasing danger. It can undermine roadways like this. It can cause houses to fall down. And in this case, it looks like the eroded material, the sediment, just kind of fell down into a wooded area, but there have been plenty of incidents where at the bottom of that slope is, say, a road or a train track or other people's houses that could then get damaged by all of that sediment coming down the slope to hit them. So climate change, by means of storms, can accelerate erosion. And then sea level rise can interact with storms. So we've talked about climate change leading to rising sea levels, and in previous lessons we've just looked at the amount by which the average sea level is going to go up under different climate change scenarios. This is relevant to storms because if you get a storm in a coastal area, those storm winds can drive that water up onto the land, and you get something called the storm surge. So if you've got winds blowing from the water onto the land, they're going to push a whole bunch of water up and raise that water level a lot more than the average calm weather water line. And so if your sea level is rising, then that means that storm surge is going to hit things higher up. So even if you've got a house there, even if your house is not going to be directly flooded by rising sea level, you may be increasingly exposed to storm surge because that water level is getting closer to you, and so it's easier for a storm to blow that water up into you, and that storm surge can do a lot of damage because that water is coming in with a lot of force behind it. It can wash away a lot of stuff, can damage infrastructure, damage homes, and destroy lots of stuff that it hits. So storm surge amplifies the problems with rising sea levels. So that is the end of what I have for you in this lesson, and I will see you next week for our final lesson of this course.